Good evening, everybody. Sorry for being late. So please tell me, can you hear me? Yes. Okay, please let me know if you can hear and see me. Okay, good. Thanks, Tejasvi and Vaishnav. So today we are going to talk about the dynamics of circular motion. So in last chapter, we studied about circular motion. Okay, and we saw that circular motion is an accelerated motion. But we did not think about from where does that acceleration comes. Okay, where does that acceleration comes from? So we'll try to answer those questions today. Okay, and there is one more topic called pseudo force. So first we'll finish pseudo force. After that we'll move on to the circular motion. Okay, so now okay, so anybody knows what is pseudo force? Yeah, pseudo means what? Pseudo means imaginary. Okay, a fictitious force. So now, where does that pseudo force come from? So let's talk about pseudo force. Now, for an example, let's consider this man who is standing in a bus. Okay, this is a bus, and man is standing in this bus, and all of a sudden, let's suppose the bus accelerates like this in forward direction. So what will happen? We know this man, he will tend to fall off, okay, backwards. Okay, so now if there are other passengers who are watching the motion of this man, so can they explain this motion? Can they apply Newton's laws and tell what's happening over here? Yeah, pseudo forces minus ma. Okay, so let's suppose there are other passengers over here. This person, okay, he is looking at this man, and he can't explain because for him the man was standing over there, and all of a sudden he falls. Okay, or he gets a jerk in backwards direction. Okay, so he cannot explain the motion of this man. So to explain this motion, a concept of pseudo force comes in. So now see, the forces acting on this man, they seem to be balanced. One force is the acceleration due to gravity, which acts downwards. Okay, and the other force will be the normal reaction due to the floor of the bus, which acts upwards. So for this person, the forces acting on this man, they seem to be balanced, and still the man gets an acceleration in backwards direction. So he thinks that there is some force, some imaginary force acting on this person which pulls him in backwards direction, and that force is known as the pseudo force. Okay, so this is one of the examples of pseudo force. Yeah. So to explain this motion of the man, okay, the concept of pseudo force comes in. So now if you are in accelerated frame of reference, this bus is accelerating, so every passenger is accelerating with the bus. So if you want to explain motion of this man, what you will do, you will apply a concept of pseudo force. Okay, so is this thing clear? All right, so let's see some more examples of pseudo force. So for an example, let's suppose we have a bus like this, okay, and there is a ball connected to a string, okay, which is hanging from the floor of this bus. Now when bus is at rest, or when the bus moves with uniform velocity, this ball, or let's call this pendulum will appear to be at rest like this. Okay, if there is some passenger in a bus who observes motion of this pendulum, so for this passenger, this pendulum will appear to be at rest if the bus is at rest, or if the bus is moving with uniform velocity. But now let's suppose this bus accelerates, okay, in forward direction. So what will happen? So this pendulum, okay, the string connected to ball, it will swing like this. Okay, it will swing in opposite direction, and if this bus keeps on moving with constant acceleration, that is a, then this pendulum will, it will come to rest at some position. Okay, so now what are the forces acting on this pendulum? So let's draw this pendulum over here. So one is obviously the acceleration due to, sorry, the gravitational force which acts downwards, and there is another force which is tension in this string. Okay, so now let's suppose the bus is accelerating with this acceleration a bar, okay, and the acceleration is constant. So now is the sum of all forces acting on this ball balanced? Okay, the sum of all forces acting on the pendulum, it's not balanced. Okay, we can resolve this tension in two components, like one component, one vertical component, and one horizontal component. So let's suppose this is some angle theta, so this angle will be theta, so this horizontal component will be t cos theta, and vertical component is t sin theta. So for this observer who is watching the motion of this pendulum, so for this observer who is inside the bus and watching the motion of this pendulum, he thinks that if I resolve the tension along two components, T sin theta will cancel out with mg. Okay, so T sin theta will be equal to what? Mg. But there is another component of tension. Okay, so there is horizontal component of tension. So if the pendulum is at rest like this horizontal component of tension must be balanced. Okay, so therefore now he applies the concept of pseudo force and he says that there is a pseudo force acting in opposite direction. Okay, and that pseudo force is, is suppose f suffix p. So how much will be magnitude of that pseudo force? The magnitude of pseudo force will be equal to t cos of theta. Okay, so t cos theta equals to the pseudo force. Now he can explain the motion of the pendulum, right? Normal reaction, I'm sorry, where is normal reaction, Tejasvi? Yes, Likit, I will complete all lessons of 11th standard physics. Yeah, it's okay. So is this clear? So if we think that there is a force acting in this direction, okay, if there is a force acting on this bob of the pendulum or that ball in this direction towards right, then we can explain the motion of this pendulum. Okay, so this force is known as the pseudo force. So now how much is the magnitude of pseudo force? Okay, so now we know what is pseudo force. Pseudo force is a force to be applied by a non-inertial observer in order to explain the motion of bodies. Okay, so pseudo forces, so how can we define pseudo force? So pseudo force is force to be applied, okay, force applied by a non-inertial observer okay, now which makes him able to judge motion of bodies. Okay, which makes this non-inertial observer able to justify motion of bodies. So we can say which makes non-inertial frame kind of inertial. Okay, so now if a non-inertial observer applies the concept of pseudo force, then he can explain motion of bodies and he can now use Newton's laws. Okay, yeah, thank you, Gangadharan. So now how much is magnitude of pseudo force? So if, let's suppose, this observer is accelerating with acceleration a bar, then the pseudo force, the magnitude of pseudo force acting on this body, okay, on this body will be equal to what? It will be equal to mass of this body multiplied by this acceleration. Okay, but now what is direction? The direction is just opposite as we have seen. So Fp bar will be equal to minus of m times a bar. Okay, so pseudo force acting on body, okay, pseudo force to be applied on body in order to explain motion of a body in non-inertial frame of reference is equal to what? Fp bar is equal to minus of m multiplied by a bar. And what is a bar? So a bar is acceleration of this non-inertial frame of reference. It's not non-inertial phase, it is non-inertial frame of reference. Okay, so see, what is inertial frame of reference? So in inertial frame of reference, an observer, he is either at rest or the observer is moving with constant velocity. So what would be non-inertial frame of reference? So in non-inertial frame of reference, observer is accelerating. Okay. The frame of reference means an observer who has access to a coordinate system and a clock. Gangadharan, is it clear? Yes. Is this concept understood for everybody? Okay. For others, is it understood? All right. So what is pseudo force? Pseudo force is a force to be applied by a non-inertial observer, which makes him able to apply the Newton's laws of motion, and then he can explain motion of bodies. Okay. So what is magnitude and direction of pseudo force? So if, let's suppose, this non-inertial frame of reference is accelerating with an acceleration a bar, then the pseudo force Fp bar is equal to what? Minus of m times a bar. Okay. So pseudo force acting on, let's say, this body over here is equal to Fp bar, and it's equal to what? Minus of mass of the body multiplied by the acceleration of this frame of reference. Okay. So now I think it should be clear. So let's move on to the next topic. All right. So now let's come back to the circular motion. Okay, let's come back to the dynamics of circular motion. So in last chapter we have studied that circular motion is an accelerated motion. So let's suppose, for an example, there is this ball or a stone tied to a string and whirled in this circle. So there is always an acceleration acting on the stone which is directed along the radius and towards the center. So this acceleration is known as the centripetal acceleration. Okay, but what would be the cause of this acceleration? So now we know from Newton's second law that a force is needed to cause an acceleration. So there must be cause of this acceleration. So that force is known as the centripetal force. Okay. All right. So now okay, am I live? Is somebody watching this? So Tejasvi, are you there? Okay, there is network issue. It's okay. So what I was saying is, in last chapter we have studied that the circular motion is an accelerated motion. So for an example, there is a body which performs uniform circular motion. Okay, uniform meaning the velocity, the speed of body is constant. The velocity will keep on changing, as we know, as velocity at different points is different. So velocity at this point is in this direction along the tangent. Velocity at this point will be directed like this along the tangent, etc. Okay, and that's why the circular motion is an accelerated motion. Okay, but we have also studied that from Newton's second law, we know that force is equal to mass times acceleration. So to cause an acceleration, we need a force. So that force over here, that force acting on an object performing circular motion is known as the centripetal force. Okay, and this is real force. Okay, this force is needed for the circular motion. So for a stone which is tied to a string and whirled in a circle, the centripetal force is provided by tension in the string. Okay, the tension in the string will be directed along the radius and towards the center. Then for planets which are revolving around sun in, let's say, circular orbits, the orbits are elliptical, but for simplicity, let's say they are circular. So for those planets, okay, the centripetal force is provided by the gravitational force. It's the gravitational force exerted by sun on the planets which pulls them along the radius and toward the center of these orbits. Then if we consider Bohr model of an atom, then from Bohr model of an atom, the nucleus is at the center, which is positively charged because of protons, and electrons revolve around the nucleus in circular orbits. Okay, so where does the force, the centripetal force required for that circular motion comes from? It comes from the electrostatic force. Okay, so it is the electrostatic force between positive and negative charges which keeps on pulling these electrons towards the nucleus. Okay, so this force is directed along the radius and towards the center, and that's why the electrons, they can perform circular motion. Okay, so a force is needed to keep an object moving uniformly in a circle, and that force is known as the centripetal force. So now we know from the last chapter that centripetal acceleration AC, the magnitude of centripetal acceleration is what? It is v squared over r, where v is the speed of particle and r is the radius of the circle. Okay, and the centripetal acceleration, it is directed along the radius of circle and towards the center. Okay, so in order to show the centripetal acceleration, the direction of centripetal acceleration, we use a radius vector r cap, but now this will be, this radius vector is directed away from center. We want this acceleration towards the center, so we put this negative sign. Okay, so AC bar, the centripetal acceleration, is equal to minus of v square over r. So this is the magnitude, v square over r is the magnitude, and it's directed along minus of r cap. Okay, and therefore the centripetal force FCP will be equal to what? It is m times AC bar, and that is minus of mv square over r multiplied by r cap. Okay, so if you want just the magnitude of centripetal force, then the magnitude of centripetal force FCP is equal to what? mv squared over r. All right, so force required to keep an object moving in a circle is known as the centripetal force. So is this thing clear? Yes, please reply. Okay, welcome Tejasvi. Now let's talk about vehicles taking turn. Okay, so let's consider motion of a car along a curved road. So here this car is moving. Okay, this car is taking a turn. So for this turn, it's performing a curvilinear motion, and we can approximately say that it's a circular motion. Okay, so now question is, for a circular motion we know a centripetal force is required. So question is, where does this centripetal force comes from? Okay, so what do you think? Yes. All right, so let's think about it. So how many forces are acting on this car? So one is obviously the gravitational force, it acts downwards. Okay, let's use this color only. So this is gravitational force F suffix g, and there is normal reaction due to the road which acts upwards. Okay, so there is gravitational force and there is normal reaction. What else is acting? There can be frictional force. Okay, there can be a frictional force acting between tires of this road and tires of the car and road surface. Okay, I think it comes due to its motion. Okay, so the car doesn't fly away in vertical direction. That means the normal reaction is balanced by the gravitational force. Okay, so we can say that N is equal to mg. But now notice what happens when a car takes turn with very high speed. Okay, so you might have seen that the car moves away. Okay, the car skids away. All right, and what is reason for the skidding? The frictional force is not quite enough to keep that car on track. Okay, so now let's suppose you are sitting in a car. So when you take a turn towards left, what happens? Okay, if you take turn towards left, you feel an outwards force towards right. Okay, so now there is no reason uh, there is no reason for this force. Okay, so when you take a turn towards left, what happens? There is an outward force acting on you towards right. Okay, so you feel an outwards force. So actually there is no force as such, no real force is acting on you. stream is buffering. Okay, so now when you take a turn towards left, what happens? You feel there is an outwards force acting on you towards right, and many times you might get, okay, your head might get banged on the window of the car. All right, so is there any force acting on you, or what's happening over here? Actually, what happens over here is you are sitting in car, and due to your inertia you want to continue whatever motion you are performing, but it's the car which is taking a turn. Okay, so you are not moving towards right, it's the car which is moving towards left, and the window of the car, it comes closer to you. Okay, but now since you are in a non-inertial frame of reference, you feel as if there is some force acting on you, and we call that force a centrifugal force. Okay, but now same force will be acting on this car. Okay, the centrifugal force, the pseudo force. So due to that centrifugal force, what will happen? The car will skid away from the center. All right, so to keep this car on the track, we need another force, so that force will provide the centripetal force, and that force is the friction. Okay, so it's the friction between this car and the road surface which keeps this car on track. So I hope you can, yeah, I think you can see this. So it's the frictional force, static friction, okay, which provides the centripetal force over here. The difference between centripetal and centrifugal force. Okay, shall I repeat this? Okay, see, what is centripetal force? Let's go back over here. So for a particle, for an object performing circular motion, we need a force which is directed along the radius and toward the center of circle. All right, because we know that the circular motion is an accelerated motion, so there must be some force acting on this object to cause that acceleration. Okay, so we know that circular motion is an accelerated motion, and there is always a centripetal acceleration acting on objects performing circular motion. Centripetal meaning which is directed along the radius and toward the center. So the force which causes that acceleration is known as the centripetal force. Okay, and this is real force. So centripetal force over here, let's suppose for the case of a stone tied to a string, it is provided by tension in the string. For planets revolving around the sun, the centripetal force which keeps them attracted towards the center of their orbits is the gravitational force exerted by sun on the planets. Okay, for an electron revolving in an atom, the centripetal force is the electrostatic force of attraction between nucleus, which is positively charged, and electrons. All right, so centripetal force is a real force, and its cause can be traced. Okay, so I hope centripetal force is clear. Yes. All right. Now let's move on to the centrifugal force. So now see, let's suppose you are sitting in a car. So that car takes a turn towards left. It takes a circular turn. So you feel, actually you will get an outwards push. Okay, sorry, an outwards pull, and many times your head might bang on the window of the car. Okay, so now you will feel that somebody is pulling you towards right. So when car is moving towards left, you will feel that somebody is pulling you towards right. But actually it's not the case. What happens over here? Okay, so this force is known as the centrifugal force. So you are in a non-inertial frame of reference, you are taking a turn. That means you are performing a circular motion, and there would be an acceleration acting on you which is directed along the radius and towards the center. So let's suppose here the acceleration is directed towards left, and therefore now since you are in non-inertial frame of reference, there is a pseudo force. Okay, so how can you explain this motion? So you will say that there is some pseudo force acting on me, which is okay, which is pushing me away from the center, or okay, towards right. All right, so actually what's happening, you are moving straight and it's the car which is moving towards left. Actually you are not going, your head doesn't go and bang on the window of car. It's the window of car which is moving towards left. Okay, so due to your inertia you keep on moving straight, but it's the window of car which actually moves towards left. So is this clear? Yeah, so very good. So now the centrifugal force that you feel, it is also felt by this car. Okay, because you are in circular motion. Okay, when you take a turn, sorry, when the car takes a turn, you are in circular motion, and that's why you are feeling centrifugal force. But what about the car? So for you, there are some forces acting on you which keep you moving in a circle. Okay, there is one force, it's the frictional force and normal reaction due to seat of the car. Okay, which keeps on acting on you. Actually, um, so actually due to centrifugal force, what will happen, you will be pulled away from the center, but it's the frictional force due to the seat and also the normal reaction due to seat which keeps you in circle. Okay, which keeps you moving in a circle. But what about the car? So for this car, it's the friction between tires of the car and this road surface which keeps this car moving in a circle. Okay, so otherwise the car could have um, skid away from the center. Okay, so is this thing clear? So yeah, Gangadharan, um, okay, good Tejasvi. So Gangadharan, there are notes. Yeah, so if you go to community tab for this channel, you will see uh, that I am putting notes for these classes. Whatever I write over here, so I put these notes on Google Classroom. Okay, the code for Google Classroom, it's given over there. So please check that. I'm sorry. Okay, Gangadharan. So I think I have uploaded notes till the last chapter, motion in a plane. Okay. Yeah, good. So now let's calculate the velocity with which this car can take a safe turn. Okay. So maximum safety speed for this car on a level curved road. Okay. So we'll derive this. Now, what are forces acting on this car? One is the gravitational force acting downwards. The other one is normal reaction acting upwards. And for equilibrium of this car in this y direction or vertical direction, so what is equilibrium? Equilibrium means net force acting on an object is zero. Okay, so the car doesn't accelerate in y direction. So for that to happen, the normal reaction must be equal to the gravitational force. So for equilibrium in y direction or vertical direction, the normal reaction is equal to mg, and we have just discussed that it's the friction which provides the centripetal force. So friction provides centripetal force for this car. So FCP is equal to what? Static frictional force between tires of this road, sorry, tires of the car. Once again I said road. Okay, tires of the car and road surface. Okay, so it is mv squared over r equals to, what is static friction? It is mu s multiplied by normal reaction, and we can substitute the value of normal reaction, which is mg. So we get mv squared over r equals to mu s multiplied by m times g. Okay, so here this m and m gets cancelled out, and we are left with v squared divided by r equals to mu s multiplied by g, which implies that v square equals to mu s multiplied by r into g. Okay, where r is radius of this curve, and therefore v will be equal to square root of mu s into r into g. All right. Okay, let me mention one thing. Maybe it might not be clear. So let me mention one thing. So now this frictional force, as we know, is variable. Okay, it is a self-adjusting force. So here we can see that since FCP is equal to the frictional force, okay, so since the friction provides the centripetal force, what I can say is maximum value of centripetal force will be provided by when friction is maximum. Okay, so we know that mv square r, so centripetal force is mv square r, mv square divided by r. So when centripetal force is maximum, the speed will be maximum. Okay, so therefore FCP max is equal to what? Fs max, and then what is Fs max? It's equal to mu s multiplied by the normal reaction. So the calculations I have done over here is considering the frictional force is maximum. Okay, so this is the safety speed limit for a curved road. V equals to square root of mu rg. So I hope this is clear. Okay, good. So now, can we rely on the safety speed limit? Okay, please tell me, can we rely on the safety speed limit? For an example, the safety speed limit, it depends upon three things. Okay, V is equal to what? It is mu s multiplied by r times g. So g is constant, it's not a variable. That means the safety speed limit will depend on the coefficient of static friction, which is mu s multiplied by r. Okay, so it depends on two things. It depends on mu s and it depends on r. Okay, so now radius of a curved road is also fixed. Radius of curvature is fixed, right? So just to increase the speed limit, we cannot increase the radius of the circle, okay, or radius of the turn. So that means now only one thing is left, which is the coefficient of static friction. So can we rely upon the friction? Obviously no, because friction is not constant. So friction between this road surface and tires of this vehicle, it's not a constant. It depends upon various things. Let's suppose the road gets wet. In rainy season, the road gets wet. Then the friction will decrease and the cars will or vehicles will tend to slip away. Okay, and it might happen that some oil is sprayed on the road and it will cause in lowering of the friction. So in that case also the vehicles will tend to slip away, okay, skid away from the center. All right, so this safety speed limit is not reliable, and that's why what we do is we use a trick. So we raise outer edge of a road with respect to the inner edge with some angle, and this thing is known as banking of roads. Okay, so in hilly region you will see that if there is a turn, then outer edge of road, it is raised with respect to the inner edge at some angle, and that thing is known as the banking of roads. Okay, so as I told, we cannot rely upon the tension, sorry, we cannot rely upon the friction. Okay, so here if we draw the normal reaction, so this is normal reaction. Now we can resolve this normal reaction along two components. So we know normal reaction is always perpendicular to the surface. So this vertical component of normal reaction will balance weight of the car, and there is horizontal component of normal reaction. Let me use different color. Horizontal component, I think everything is same. The horizontal component of normal reaction, it is directed towards the center of circle. So this horizontal component of normal reaction provides the centripetal force. Okay, and that's why now the cars can take safe turns. Cars or vehicles, they can take safe turn. So is this thing clear? So raising of outer edge of a road with respect to the inner edge at some angle, it is known as banking of roads. So banking of roads, it is done to ensure safety of vehicles. Okay, yes, is this in clear? Please reply. How can we say that horizontal component of normal reaction becomes centripetal force here? Yes, see here. Okay, the curve is like this. Okay, so we can figure out in what direction this horizontal component of normal reaction will be directed. It will be directed towards the center, and that's why we can say that it provides the centripetal force. Okay, just to give another example. Okay, good. So now next thing we'll do is we'll derive an expression for the safety speed for curved banked roads. Okay, so let's consider motion of this car along a curved road which is banked. Okay, so this much is banking. Yeah, and the road is curved like this, something like this. Okay, so now let's draw all the forces acting on this car. So what are all the forces acting on car? One is normal reaction. We know it is directed like this. This is normal reaction. Then next thing is the gravitational force which acts downwards. Sorry. So gravitational force is mg. And now in what direction this this car will tend to skid? Downwards on this incline or upwards up the incline? Yes. Okay. We know, no, not down. In ordinary conditions, it will tend to skid down. If we just keep that car on that incline, it will tend to skid down. But now what's happening? The car is taking a turn. Okay, the car is taking turn. The center of that car is directed something like this. Okay, so we know that the vehicles tend to move away from center. Okay, if center is directed like this, the vehicle will tend to skid away from the center. So it will tend to skid like this in this direction. Okay, so if it skids in this direction, what will happen? It will skid up the incline, not down the incline. Is it clear, Tejasvi? So due to the centrifugal force which acts away from center due to a pseudo force, okay, it will tend to skid up the incline. All right. Banking means, see, this is a road. Raising of one side of road, one edge of road with respect to other edge at some angle. So this angle is suppose theta. So raising of one end or one edge of road with respect to the other edge, with respect to the other edge at some angle is known as banking of roads. Okay. Okay, good. So is this understood now that it will skid up the incline? Okay, good. So in what direction the frictional force will act then? The frictional force opposes skidding, and therefore it will act down the incline, okay, along the surface of road, act like this. So this is static frictional force. All right, and this angle over here is theta. So now we have mentioned all the forces. So we have mentioned all the forces acting on this car. So now let's derive an expression for the maximum safety limit, safety speed limit. So I will redraw these forces over here. Yes. So here I will denote this car using a point, okay, and then I will mention, I will draw all the forces acting on this car. So this is frictional force, then there is gravitational force acting downwards, and there is this normal reaction which acts like this, okay. N, Fs and Mg. So now since this angle over here is theta, I can say that this angle will also be theta, and this angle, sorry, this angle will also be theta, okay. This angle is theta, so this one is just, these are two parallel lines and this is an intercept, okay. So this angle is theta, and this one, this angle is 90 degrees, so this is 90 minus theta, and that's why this angle is also theta. All right, so now the center of this circle is directed something like this. So we want the centripetal force in this direction, okay. The centripetal force which will be provided by resultant of these forces, it is directed like this. All right, so now let's resolve N, the normal reaction, and the frictional force along two perpendicular components. So this component over here will be N cos theta, and this component will be N sin theta, okay. Similarly for Fs, this component is Fs sin theta, and this component is Fs cos theta. Now we can look at all these components and we can write down conditions for the equilibrium. So for equilibrium, of this car in vertical direction, what I can say is the vertical component of normal reaction n cos theta should be equal to fs sin theta plus mg. Okay, so net upward force is equal to net downwards force. So n cos theta must be equal to fs sin theta plus mg. Okay, and I can rewrite this expression like this: mg is equal to n cos theta minus fs into sin theta. So let's call this expression 1. After that, over here, this n sin theta and fs cos theta, they are directed in direction of let's say along the radius and towards the center. Okay, so n sin theta and fs cos theta, they combined provide the centripetal force. So centripetal force is provided by the horizontal components of the normal reaction and the frictional force. So I can say that FCP, the centripetal force, is equal to n sin theta plus Fs into cosine theta. All right, and centripetal forces mv squared over r. So mv squared over r is n sin theta plus Fs cosine theta. And now we want maximum speed with which this car can take a turn on this curved banked road. Okay, so for maximum speed, which things we can change on right hand side? There is only one variable, and it is the frictional force. Okay, so just like the last case, just like the case of the level road, let's make this Fs max. So let me call this mv max square or r. It will be equal to n sin theta plus, this will be Fs max multiplied by cosine theta. So let's call this equation number 2, and now equation 1 can be rewritten for the case of maximum safety speed. So in equation 1 only Fs will change to Fs max. Okay, so I can say that from 1 mg equals to n cos theta minus Fs max into sin theta. All right, so let's call this equation number 3. Then we know what is Fs max. It is just mu s multiplied by the normal reaction. So let's substitute that in equation number 2 and 3. So substituting that, what do we get? So from equation 2 we get m v max square over r is equal to n sin theta plus Fs max into cos theta. So it is mu s multiplied by normal reaction into cosine theta, and from third equation I can say mg equals to n cos theta minus mu s multiplied by n into sine theta. Okay, and after this what I will do is I will divide this equation which I got from equation number 2 by the equation which I got from equation number 3. Okay, so let's divide these two. So we can just say it is equation 2 divided by equation number 3 because we have just put mu s times n in place of fs max. Okay, so if we do this division, we get m and m gets cancelled out over here. Okay, so V max square divided by Rg equals to, on right hand side we get I'm sorry, we can take n common from all terms and we can cancel it out. Okay, n is present in all terms on right hand side in numerator as well as denominator in denominator, so we can take it common and cancel it out. So what we are left with is sine theta plus mu s times cos theta divided by cos theta minus mu s times sin theta. Okay, and now if we just divide the numerator and denominator on right hand side by cos of theta, what do we get? So sin theta divided by cos theta is tan theta plus mu s multiplied by cos theta divided by cos theta is 1. So tan theta plus mu s divided by, in denominator, okay, so let me write this step. This is dividing numerator and denominator on RHS by cos of theta. Okay, so what do I get? We get V max squared over Rg equals to, on right hand side, sin theta over cos theta is tan theta. So tan of theta plus mu s multiplied by cos theta divided by cos theta is just mu s. Okay, and in denominator we have cos theta upon cos theta, so that's 1 minus, okay, mu s multiplied by sin theta over cos theta is tan theta, so mu s tan theta. And then what we can do is we can take this Rg on other side of equation and then we get V max squared. Okay, so V max squared equals to Rg multiplied by, we have mu s plus tan theta or tan theta plus mu s divided by 1 minus mu s tan of theta. Okay, and then if we take square root on both sides of this equation, so on left hand side we'll have I'm sorry, on left hand side we'll have V max and on right hand side we'll have square root of Rg multiplied by, in bracket, mu s plus tan theta divided by 1 minus mu s tan theta. So this is the maximum speed with which a car can take a turn along a curved banked road. Okay, so is this thing clear? Yes? Okay, good. So now let's suppose that there is no friction at all. Okay, so let's consider the special case that mu s is equal to 0. So let's make all terms in numerator and denominator 0 where we have mu s. So if we do that, we get V max equals to square root of Rg into tan of theta. Okay, so this means that even if mu s is equal to 0, even if there is no friction at all, what happens? We still have some maximum safety speed limit. Okay, so we can still drive our car or our vehicle along that banked curved road with this much speed. Okay, this is maximum speed. So this speed or below this speed. Yes. So this is the use of banking of road, raising one edge of a road with respect to other edge at some angle. Okay, then let us stop at this point. So next time, I think the chapter is over. Next time we will do some numericals on this chapter. Okay, good night.